Hello guys, in this video tutorial series, we are going to talk about artificial intelligence, data science, data engineering, machine learning, and LLMs, and mostly practical examples with theoretical understanding. Okay, so today's topic is bias and variance trade-off, understanding between the difference of bias variance in any particular machine learning model, and we think that it's pretty much important for you to understand and to grow as a machine learning engineer with the basic objectives, right? What needs to be right, because the fundamental of any model is same, right? So we'll go deeper in the fundamentals with practical implementations, as well as then we'll climb up all the complex models one by one with practical implementation and deployable projects. Okay, so what is bias and variance trade-off, and what this thing, from where it comes actually, right? So have you ever trained a machine learning model, right, that performs, let's say, well on your training data, but fails on real data, right? Or maybe model that does not learn anything at all. Okay, so that's where your bias and variance trade-off comes out. That means you have a model that probably are performing very well on your training data set, but is failing. So let's say archival competition you are participating, right? So whatever model you have built, it's performing very well on the training data set, but when you are submitting your test score, right, or whatever your achievement, that ranking that they used to show, there you are getting a very less rank. Okay, that means from rank wise it's higher, from score wise it is lesser. Or you build a machine learning model, let's say, that is not learning at all anything. Okay, so this is the place where your bias and variance will come. Now let's start one by one. What is bias? What is variance? Okay, how to balance out between your bias and variance within any model for better improvement, or uh, whichever you understand, right? And the final one will be your let's say small real time example. And in this channel, okay, most of the examples will be covering mostly within stock market or trading, mostly, as particularly have a very keen interest there. So most of the examples we will try to cover using trading examples, real life trading examples. Okay, so first let's go for bias. So what is bias, right? Bias is nothing but your oversimplification of assumptions in a model. Okay, so that means bias you can understand in a class, the backbenchers who does not learn anything during the class. Okay, so what material they will consume after those 90 minutes of class? Zero, right? That is what bias is. Bias means oversimplification of model. So whatever you will get after doing oversimplification is bias. And variance means you can consider the first benches, right? Those guys who comes 10 minutes before the class, leaves 20 minutes after the class, having 20 odd doubts in between the classes. Those concepts are practically, you can consider as variance. Okay, so it's pretty much simple. What is bias and variance? So bias is oversimplification of model, and variance is more, I mean, advanced complication of models, right? That means model is trying to learn each and every parameter. Okay, so what problem you will face if you have a high bias model, right? That means let's say you have a parabolic model, right? The model follows let's say y equals to 4ax square, right? This kind of equation. But instead of building a model like that, you are building y equals to mx plus c. That means you are building a straight line. So let's say you have a parabolic curve, so you have to take turn, right, at the curves, but your model is a straight line. So if you, in real life, let's say you build a Tesla that's going straight instead of going parabolic, what will happen? You will end up with accident. That means in machine learning term, you will end up in errors, right? So that's what happens when you do oversimplification of model. That means bias, right? That means what is the effect of high bias here? High bias has too simple, model will become too simple, that fails to learn the actual pattern. So here the pattern is parabolic, but your Tesla is learning a straight line. So very simple. So you can understand it like a kitten, okay, 2 or 3 months old kitten, and it will what implication it will have technically. So here you have to understand these technical terms that might be asked in your interviews. Most people will also search in ChatGPT for questions. So yeah, so you will have a high test error as well as high training error. So that's how you will understand your model have high bias problem. That means your training also will have high errors. Your testing will definitely also have high errors, right? So that's what your bias is. And your variance means trying to killing the bias. That means oversimplification of model is bias, and complexity basically is what your variance is. So what will happen in case of variance? It will try to capture all the small variation or fluctuation of the data set, basically the training data set. That's what is variance. Okay, so in case of high variance, your model becomes too complex and it becomes too much sensitive with the smallest sense of fluctuation in the data. Okay, so how you can imagine it as a real life example? Let's say same parabolic curve, right? But instead of going parabolic, you are going x to the power 10. Let's say power of 10. You are going. So even a small curve when it will come. So let's say in case of trading, I find trading much fascinating. So in case of trading, if you are a overthinker, so complicating a model is nothing but doing a overthink. At every 5-minute candle, by predicting the candle's shape, size, and whatever it is coming, right? You are trying to predict the next candle, and in that case, you are taking a lot of trades, right? And at the end, you will end up blowing out your account. Whether if you can understand the pattern, you have taken a trade and you have just waited for some time, you will probably gain some money, or will probably succeed in that particular session, right? So that's what your overcomplication happens, and your overcomplication equals to high variance problem. Okay, so your high bias problem means simplification, high variance means complication. Okay, so how to understand your high bias and variance in code? Python will just simply quickly go here. So here you can see all, by the way, all these codes are available under this GitHub. So I'll add this GitHub link there so that you can easily see all the codes that we're going through. So you don't have to write any code, you just understand, play with the codes. You can download in your free times. Okay, so first, yeah, we're just importing NumPy, Matplotlib for plotting, and scikit-learn for this simple linear regression model utilization, as we are not interested in writing linear regression models. Okay, so here we have x and y. So x will be our input and y will be the output, and both in combination will be our data. So x is nothing but from -3 to 3 we are creating random 100 sample data, and y is our x cube plus some random noise. Okay, so it's nothing but a cubic function plus noise. Okay, so y equals to x cube plus epsilon, something like that, you can understand in that manner. Okay, now if you print x, so as I have mentioned, x is nothing but a linear space between -3 to 3 within 100 dots. So -3 to 3 in between you can consider 100 dots, and that's what your x is. Okay, just give me a second. Yeah, so that's what your x is. So now if you do x cube and y, so here you can see particularly in this point, you can see your x value, x cube value is -27, and y first value of the y array is -24. So this deduction or this changement between these two values is happening because of the noise, right? Because as per the conviction here, my y is nothing but x cube plus noise. Okay, now this is you will get if you use this functions, that np.random.normal, and you use a scale of 5, then you will get a value like this. So if you hit again, you will just get another changed value. Okay, so you don't have to worry about all of this. and this is the first 5 y values you can see in the form of array. Now first we'll have to create one linear regression model. So let's create model equals to linear regression, then we'll have to fit the model, and then we have to predict for y by providing x. So we're doing the 3 steps here. Okay, pretty simple till now, right? Now the next thing what we'll do, we'll just do a simple plot. So what we're doing here, so we're doing a scatter plot between x and y, and we're keeping the color of the dots as blue. Okay, and this is we're labeling as true data, complex data that we have created between x and y. That means a cubic relationship with noise. Okay, so if you can see, it's something like this, a cubic relationship, and the plot is simply a linear regression model, right? A linear plot, and the plot color is red. Okay, so this is, you can see, this is a linear model and true model, right? So this is what your high bias looks like. So if you're data is pretty complex, you're trying to fit a very simple for every, it's like, let's say you have a MCQ and you are answering B, A, B, C, D is your choice, and you are answering B for all it. So let's say there is 25 or 26 question that actually has a B as correct answer, right? So you'll get 26 marks out of 100. Okay, now next step is your high variance. Okay, so variance will come when you increase the complexity. Okay, so instead of straight line, it will have a very curvy lines. Okay, so the same thing we'll see here. So here we are just importing polynomial features from pre-processing of scikit-learn. Then we are also importing pipeline for building one pipeline from scikit-learn.pipeline module. Now first let's keep the degree as 3, as we are trying to we already know, right, that whatever data we have built is a cubic data. So we are keeping the degree as 3. We are just creating one pipeline where we are passing this polynomial feature with the corresponding degree and linear regression model. So it will create polynomial features. Okay, it will create x squared, x cubed, something like that. Then we are fitting the model, and then finally we are doing prediction. Same 3 steps, right? Instead of linear model fitting, we are just fitting one polynomial. Okay, so once done, same plotting we are doing. So you can see that this is the linear model, and now here this dotted green line is our cubic model. So this is kind of a very good fit, right? If you do the error calculation, you will find this fit is more accurate than this fit, right? So this is a far better model compared to this one, that linear model one. Okay, so where this trade-off comes between bias and variance. Okay, so finding the right balance between bias and variance is often become very much important for any machine learning model, right? So no matter what, right now it's a linear regression problem, you go to decision tree, you go to SVM, you go to more complex, neural networks, transformers, LLMs, all these steps. This is a pretty common step, right? Your bias and variance predictions, trade-offs. So for finding a correct balance between bias and variance is pretty much important in any machine learning project. Okay, because the target here that we wanted to keep the bias is low as well as the variance is also low. Okay, what is the analogy here? If you have a high bias, that means your model is trying to learn nothing, and if you have a high variance, your model is trying to learn everything. That is the analogy here, right? So we have to find one balance where your model will learn just the exact thing it needs to learn, so that the error will get minimized, right? Now, so solution, how you are going to generalize the thing, how you are going to decrease if your model has high bias. So in that case, we are going to increase the model complexity, right? So if you have a straight line, you'll just trying to add some polynomial features like x squared, x cubed, something, and you will see if the model is getting performing better. If you are training for, let's say, 10 times or 10 epochs, you are going to increase the number of training. So let's say previously you were trying to train, let's say, 100 cycles, you increase the cycle to 200, 300, and see if it is improving the bias. That means it is decreasing the number of bias. And the third one is you will add random more features. So these are pretty straightforward process that you can do to decrease your high bias problem. And similarly, In case of high variance, what you can do, in case of high variance, you can use regularization technique like L1, L2. We'll be discussing regularization in another video, what it is, how to use regularization for neural network, for normal machine learning models, for LLMs and all. Then you can get more training data. So if you have a high variance problem, data insufficiency could be one of the cause, so you have to get more training data. And the third one, you can use cross validation in validation phase, right? So we have training, validation and testing phase. So in validation you use cross validation, you will see definitely see a decreasing rate of variance. Okay, now a real life example will be, let's say, as we have already mentioned, that we are going to every real life example, mostly while explaining part, we are trying to use stock market and stock market examples. So let's say in case of predicting stock market price, if you use a linear model that does not include the trend or seasonality or cyclicity, whatever is available for that stock, right? So it will not give you a correct prediction, and your money will be wasted. So let's say a point where the actual prediction should be sell, your model is keep on buying, and you are buying on every dip, and you are losing all of your money just because your model is overly simplified. That means high bias model. And the same thing goes for high variance as well, that it tries to capture all the noise of the stock market, and you end up losing money. That same example I just tried to plot here, right? So here you can see again random seed, so that you can also meet the same set of numbers that I am currently seeing here. And here again x is nothing but your -3 to 3 with a reshaping of -1 to 1, so it's just a reshaping factor. Then you are getting y equals to some x square minus 2x plus 1, some quadratic function plus noise, right? So it's f of x square. And then you are now here same with the help of make pipeline method, you are creating some same polynomial regression method with a degree of 2. And then you are again complexifying the model, this polynomial model, by using a degree of 10. So here you are using degree of 2, here you are using degree of 10, and then you are again doing the same fit. Okay, and once it is done, you are just plotting, and here you can see this is your data points. Your true data are represented by these blue dots. Then your green one is your simple fit, that means quadratic fit, right? As your function is also, actual function is also quadratic, right? X square minus 2x something, right? So you can see it is giving a very good fit. But if you do a very complex model, it is going through all the data points, as you can see here. But what it is doing, it is complexifying, so it is increasing the variance part of your model. Okay, so this is also not a good model, no matter how complex it is. Okay, so sometimes overthinking or over understanding or overachieving is also not good. So this is what your high variance problem is. Okay, and now we are just showing you the example that we have just discussed about the stock data. So here you can see we just taken 20 simulation days, day 1, day 2, day 3, day 4, and let's say it has a random nifty value, nifty 50 index. It's stock index of Indian market managed by NSE. So if you are a BSE fan or crypto fan, you can change it to Nifty close, to change it to Sensex close, or BTC close. Okay, so you can see this is the time frame, and this is the Nifty closing values. So we'll have X, that means the days, number of days, and we'll have Y, that means the predictions. Okay, so it's a univariate time series prediction basically. So we'll just do a simple linear regression model fit here. Okay, and in case of complex model fit, we are going to do a polynomial feature fit. Okay, same thing. And if you do a plotting, you can see it's all the days, trading days values. Okay, so all the days values, and you can see your high bias problem or high bias model is nothing but a simple straight line near about the mean, and your high variance value is very volatile model. Basically, it's trying to learn all the noise and all the fluctuation, which it should not, right? So this is the problem with over complex and oversimplified models. Both can give you a huge setback if you are going to implement these things without properly evaluating. Okay, so that's it for your bias and variance problem. I hope you have understood and learned something new here. So if you have learned something new, just try to give a quick thumbs up. And here you can now you'll see a three similar kind of application that I have built for understanding. You can download all of this from the GitHub and play with it. So this is a bias variance trade-off demo where the code you can see here. Okay, so in base you can see it's nothing, same data that I have taken, but here instead of y equals to some quadratic or some polynomial features, we have taken a sinusoidal function. So you can see here, right, it's the true function. This green line is a sinusoidal function. So what we are doing, we are just getting the data, we are doing a polynomial fit, we are doing a linear fit, and then whatever we are trying to do bias variance estimation based on the degree of polynomiality. So if you oversimplify the polynomial degree, you will see your model becomes overly simplified. That means a straight line with a polynomial degree of x. Okay, and you can see the bias value is very pretty high, 0.18, and variance value is 0.27, and total error is nothing but summation of both the stuff. And if you increase the polynomial degree to, let's say, 15, you can see a decrease value of bias and increase value of variance and the total error. So our target here, and you can see it's mostly accurately fitting the data, but it is getting over complex. The value is getting over complex. And here you can see this is your total error, how your total error got changed with the value of model complexity and bias terms. Okay, so it's practically a U-shaped curve, and your target is to come into this particular portion where your error will be minimized. Okay, so if I keep it as middle portion, I can see again, right, this model with 8 degree, model with 10. You can see all the bias and variance. You can play around with it. Okay, similar thing that I have built again here. This is another application where it will give you all the bias variance breakdown here along with this bias variance trade-off curve, and you will have a little bit understanding from this lesson that your low complexity means underfitting means high bias low variance, high complexity means low bias high variance, optimal model means there is no error or minimized error. Okay, and here also you can see the same thing. Low complexity means high bias low variance based on the current selection. Okay, so if I go again, so I will see that same thing. Low complexity means high bias and low variance. Okay, and this is the fit, similar whatever we have seen in base 1, right? And now if I just increase it, so I will see this is high complexity, that means low bias and high variance, and I can see the complexity increases in the red dot format. Okay, and if I just do a balanced approach, as I know it's kind of a sinusoidal, right? You can see a balanced complexity where it is more or less accurately predicting the function or learning the function. So this is how your bias variance will come, and this is how your error fluctuates with bias and variance. It's kind of a U-shape trade-off curve for every model. And the third one is it's just to inform that these are the examples where we have taken simple linear regression and polynomial regressions, right, for showing. But this same concept of bias and variance is valid for your complex architectures like LLM, what LLM supports, like a transformer. So here is the example where I have taken one simple transformer model where you can see this. We'll discuss all of this when we'll be dealing with transformers and all. So here you can see it's a simple transformer model, and with the same data set kind of a thing, right? We have built the data again. It's a number of heads, attention layer, hidden dimensions and all are mentioning. So we'll discuss when we'll be dealing with transformer. In that class we'll discuss how to build transformers, what are the basic building blocks, how transformer reacts and all. And here also, if you train the model for 20 epoch and you do a plot, similar kind of plot between bias, variance and all, total error basically, so you will come up with something like this, that bias variance trade-off in case of transformer, where you can adjust the attention heads, you can adjust the transformer depth, you can adjust the hidden layer. So let's say right now the hidden layer is 64. What will happen if I increase the hidden layer to 256? Okay, so that means the number of layers got increased a lot. So you have to give it some time, because you are running a deep learning model, right? No matter how small the data is. So here also you can see the complexity is balanced. You can see the bias value, the variance value, the total error, and you will see a trade-off curve will get changed. It is again a U-shaped curve, right? As you can see. So let me just wait for this bias and variance trade-off curve to show up here. And you can here also, you can see this is a true function and how your transformer model is learning, right? How your transformer model is learning based on the number of attention head, transformer depth and hidden layer size selection. Okay, so the idea is not to understand or go through about transformer, but to see, okay, no matter whether it's a complex neural network or simple tree method or a very simple basic linear regression, you have to come to the same approach of bias and variance, where if your model becomes too complex, you will have high variance problem. If your model becomes too simple, it will be a high bias problem. Okay, so I will not wait for this to complete. I think you can download and play with it, okay, alongside following this video. It will, okay, it has come. Now you can see, okay, the shape got changed, right, based on the number of hidden units, but you pretty much get the gist, right, out of what we are trying to discuss here. Okay, here also you can see it's a U shape, right? So that's it for this video regarding bias and variance and how to manage bias and variance. This is pretty much the first class with practical examples, where we have done 3 to 4 hands-ons, and our target in the next class will be exploring probably different topics of machine learning, where we'll be discussing the same thing with practical examples, and obviously most of the time the niche will be trading. Thank you very much for joining me. Goodbye.